So thank you, Jose, for this introduction. I would like to thank ISGAN for hosting this webinar and welcome all the participants today. I'm going to present in the first part the Smart4RES project and the challenges we address, and then I will pass the floor to Pierre Pinson to present research for innovative weather and renewable energy sources production forecasting products. Seems that it's a bit slow in changing the slides.
Okay, maybe you can, okay, here it is.
So we can say today that renewable energy sources forecasting is a quite mature technology with operational tools and services used by different actors like system operators, trader, utilities, and others. However, there are several gaps and bottlenecks in the model and value chain of renewable energy forecasting, stimulating significant research worldwide. We can see here, for example, in the figure on the right, that just in 2019, last year, we found in Scopus something like 500 papers on wind and solar forecasting. So the objective of the webinar of today is to present the challenges and innovative research towards a next generation of tools for renewable energy forecasting and related decision making. So we spoke about Smart4RES. What is Smart4RES? It is a new collaborative research project aiming to give a new boost to the RES forecasting technology through some disruptive ideas. It is a project which is supported under the Horizon 2020 program of the European Commission with a consortium of 12 partners from 6 countries. It's a multidisciplinary project that started last November for 3.5 years. So I spoke about the model and value chain of renewable energy forecasting. First of all, we are interested of weather-dependent renewables like wind, solar, run-of-the-river, hydro, etc. At the first step, what we have in this value model chain is the data, which can be either measurements from the renewable power plants or weather stations, or like power measurements or weather variables, or information from remote sensing like satellite images, sky cameras, radars, lidars, and others. Then at the first step, modeling step, we use this information to generate weather forecasts for weather variables by numerical weather prediction model, and here this is usually the task of meteorologists. Then these forecasts are used as input to models that forecast the output of renewable power plants production for the next minutes up to days ahead, and then this information is transmitted through services or data platforms to end users for using them as such or in functions like storage management, reserve allocation, predictive management of renewable plants, trading to the electricity market, economic dispatch, scheduling, congestion management. So any functionality related to power system management and electricity markets. As I said, this technology is considered as quite mature, but the accuracy remains, however, low. And the impact of that is that we can have financial losses in electricity markets. We can have an increased need for costly remedies like reserves or storage or demand response solutions. We can have a limited capacity of the renewable plants to deliver reliable ancillary service to the grid. So this means to behave like conventional units. We can have lower acceptability by operators because they may not have so much the delivery of the renewable plants, or curtail renewable generation by operators and others. On the other hand, there are some new needs for forecasting products that are emerging from new applications, like, for example, forecasts for aggregated renewable energy production, or forecasts for net load at different points of the grid, or dedicated forecasts for ancillary services provision. This is not actually the forecasting problematics that we use in a classical research, where we can have a kind of vertical research dedicated to wind forecasting or solar forecasting, etc. So the vision of Smart4RES is to achieve an outstanding improvement in the predictability of renewable generation through a holistic approach that covers the whole model and value chain related to renewable energy forecasting. And to do this, we have defined the following objectives. First of all, we consider the whole value chain and model chain to define requirements for forecasting solutions that can be adapted to a future context, not only the context of today, but to a context where we are going to have a very high renewable energy penetration to the energy systems. Then the aim is to improve weather forecasting, especially dedicated for renewable energy applications by, let's say, 10–15% using various sources of data and very high resolution approaches. A third objective is to develop a new generation of renewable energy production tools for forecasting, enabling at least 15% of improvement in terms of performance. And then to streamline the process of getting optimal value through new forecasting products, data marketplaces, and novel business models for the various steps of this model chain. And when it goes down to decision, we want to develop new data-driven optimization and decision aid tools for power system management and market participation of renewables, which try to increase the value that we can have from the use of forecast in this decision making. And finally, the last objective is to validate all the new models through living labs, real installations at real wind farms or renewable power plants, and assess the value of forecasting versus remedies like storage or other. So now I will speak about the challenges that we address in this project. With our partners, we have first analyzed the different gaps and bottlenecks we can find today, both in the academic state of the art and also in the industrial use of forecasting tools. And we have identified a number of challenges. First of all, it is important to develop numerical weather prediction products which are adapted to the problematic of renewable energy. So far, weather forecasts are addressed to any domain, aviation, navigation, etc. For this, a first step is to improve the prediction of some variables which are important for renewables, like, for example, solar radiation through improved modeling of the cloud radiative impact through dynamic consideration of aerosols, for example. Then we know today that weather institutes have different models for different time frames, for the short term, longer term, and in the applications we need to take decisions for different time frames, and often we have discontinuity. So one of the objectives is to develop seamless weather predictions for the different time frames so that they can be used in a more easy way in the different applications. Then a common need that comes is that we need to increase spatial and temporal resolution and updates frequency of the weather predictions. And this can be possible today thanks to computational capacity and new modeling tools. Finally, so far we have used remote sensing tools and new information sources to improve modeling of weather variables, but now we try to increase it, to change a bit the dimension. And for example, here in this project we consider, let's say, one of the cases a network of cameras where we try to have a very detailed representation of the sky conditions, for example, in a large area. So this somehow changes the dimension in terms of information we can have in real time about the weather conditions. Another important point is the limitation of the prediction models today, the renewable power prediction models, to explain large amounts of heterogeneous data. The state-of-the-art consists of separate models dedicated to different time frames. For example, we develop models for the 5 minutes to exploit information from sky images, or a dedicated model for the day ahead to exploit information from weather forecasts. However, as I said before, for the weather forecast, necessary to use forecasts for different applications simultaneously for different time frames. So there is a need for seamless and also quite generic forecasting approaches, generic in terms of technologies, I mean wind, solar, or aggregations, able to consider simultaneously heterogeneous data from different sources. So the big question is, can we possibly speak about a convergence of forecasting solutions to simplify the model change that we have today? Here we have an example, for example, where we can have very short-term predictions using sky images and data for the first hour, or then satellite images for the next hours, up to 6 hours, and then weather predictions up to day ahead, and then we can see the discontinuities we can have. Another aspect that we have observed is that there is a kind of open loop between the forecasts, the processes that generate the renewable forecasts, and their use in applications. So we have developed an idea to close this loop, actually. So far, the renewable forecasting models are centered on improving and tuned on their accuracy. Here we can have a scheme where we have a number of models that can be used, forecasting models for renewables or electricity price, that can be used as input for trading, and the decision is to the bids to the market. However, an alternative approach could be to tune the models considering not only the accuracy, but also the value they bring to the application. And for example, in this case, it's the revenue from trading. So tune the forecasting models and the price forecasting model as a function of the end result. And why not go further to a kind of more disruptive approach where we could use artificial intelligence to simplify the whole model chain? So why not replace all these forecasting models and the decision making step of stochastic optimization by a single model, which could be probably based on artificial neural networks? And this means that, for example, in a process where we have an aggregator of a virtual power plant who participates in multiple markets like day ahead and ancillary services, we could replace something like 13 forecasting models and needed for predicting the production plus the market quantities and to decide on the bid by a single model. So this is a quite new direction. Then we are observing today that there is a decaying commercial value of forecast products that somehow is not motivating for improving the forecast quality or the research. On the other hand, there is a kind of lack of open data, often because of privacy and confidentiality issues. And there is a lack of price incentives to share data. So how can we extract value from the data, actually, in an era where we speak a lot about energy digitalization, and the focus is on collecting more and more data. But what real value can be extracted from the data? So many works have shown that we can have real benefits of integrating spatially distributed information, for example, from neighbor PV or wind farms as sensors, to improve the predictability of a single wind farm or a PV plant. And we can have an improvement up to, let's say, 20% for the first 6 hours, compared to models that do not use this information. So with Smart4RES, we will exploit data science techniques like federated learning to develop a framework for collaborative forecasting through data sharing that respects privacy and confidentiality constraints. And we will go further to develop a kind of data market concept to foster data sharing. And Pierre will speak more about this later. There is also a lack of standardization that complexifies this model chain, but I will not develop this here today. And finally, when we go to decision making, there is a need for decision aid tools adequate for high renewable penetration scenarios. And there is also a need for business cases that demonstrate the value of integrating uncertainty and probabilistic forecasts to the business processes of the industry. So in this project, we consider a number of use cases where we use forecasts for power system management or market participating. And I have already mentioned some of them. So here is a list. Like, for example, we have the collaborative forecasting use case where we try to extract value of the data. We have the trading of renewables and special virtual power plants to different markets. We have provision of ancillary services, the concept of data markets, predictive management of the grids with grid state forecasting, voltage control and congestion management with focus to isolated insular system of islands, storage optimization, coupled with renewables and others. So this is the first part of the presentation. So I will pass now the floor to Pierre to present research and innovative weather and rice production forecasting products. So I will stop sharing.
Thank you very much, George. Yeah, you need to pass it on to me. Thank you very much. I'm gonna start my presentation from the slide. All right. Okay, so now normally everybody is able to see my presentation too. So thank you for the introduction and thank you for this very nice overview, George. One thing I picked from one of your slides, since I'm going to talk about forecasting products, is that maybe in the future, one of the products is that we don't have forecast anymore, which I don't know if it's a good piece of news or it's worrying. I think it's one approach, but that's what we'll be discussing in the future in the next slides. Actually, there are many different ways we can conceive forecast products, and it will depend on maybe the level of expertise and the needs of the forecast users. So here, really what I want to start with is the idea of what is a forecast product, right? Because a lot of us in the R&D side or on the industrial side, practitioner side, we are used to these products. Maybe we don't really think much about what they are. And a forecast product really in practice, that's the interface between all the work that's done with data. So that's the data science part, the physical modeling part, etc., and the forecast user on the other side. So here, that's what I try to represent. And really maybe the key word here is at the bottom right of the slide, is that more and more what we all do is that we go towards a more problem-oriented approach. And that means that the forecast product actually a way to tune and massage the information from all these sources that are on the left so that it becomes the most useful way to transmit this information to the forecast user to be used in decision-making or as a support to decision-making. Most of the type of input for a forecasting product, they are there on the left. There's obviously all the data streams. We are collecting more data than ever. If you were to compare with the more focused field of meteorological forecasting, you know, meteorological forecasting has been collecting so much data from planes, from boats, from everything, satellites, for decades now. And it's something we see, I think, appearing more and more also on the energy side. Now there's much more use of remote sensing. People can issue their weather forecast themselves, etc., etc. So there's so much more in terms of data streams. Modeling also, now it's really not rare that people use many models as input to forecasting. And so then if you have a lot of output of models, you need also to blend this information into a forecast product for the forecast user. There's forecasting expertise also depending on the expertise of the modeler and forecaster. There might be different type of information as output. Again, it would have to be channeled through a forecast product to be the most useful information for the forecast user. And finally, one thing I think we need to remember, there's a lot in terms of analytics and visualization. So their analytics, I think, more of the problem, the decision problem at hand. George mentioned a few of those problems and the fact that some of the forecast users may actually like to have automatic decision making and visualization also. You will see in some of the next slides some basic visualization, but still we see today that there's a very big power of visualization in the way the forecast users will understand, appraise, and use a different type of forecast product. So if we were to actually try to understand what's going to motivate new forecast products, I was telling you it's a problem-driven approach, but it's actually a bit more complicated and broader than that. We see 4 pillars that really motivate this new research and work on forecasting products. One that is really clear, especially in Europe, but I'm sure it's the same in many other areas in the world, is that there are changes with the regulatory and market framework. There's a lot of discussion about peer-to-peer markets, flexibility markets to support integration of renewables. There's discussion about new market products for ancillary services, for short resolution electricity market. And there's also new requirements from the regulatory side to support integration of renewables, but sometimes also maybe to put some kind of extra constraints on the renewables to make sure that the system is not at risk when we integrate them. Right? So you have this one pillar on the regulatory and market framework. It definitely is a big driver for new forecasting products. I'll give you an example afterwards. For now, I'm going to go through these 4 pillars. Another pillar is technology and its development. I mean, we really see that the landscape in terms of assets is evolving a lot lately. We have larger wind turbines. So this was some of the work some of us have done in the past. You know, we've been claiming we should not have a single weather forecast, for instance, a wind speed forecast at 10 meters above ground level. We need a forecast for several levels to actually span the whole height of the turbines. And today we discuss even having some wind profile forecasts that are really specialized and tuned for offshore wind farms. There's also hybrid power plants. There's so much discussion about blending wind, solar, and storage. But then we need to adapt our forecast methodology to blend also all the information we can have of these different types of assets. There's these prosumer setups, again, back to this peer-to-peer idea that is becoming very, very hype, and maybe more than just hype, it's also coming for real. So in this prosumer setup, then we're going to need forecasts maybe for net load at a household level or at a small business level. And then we're going to need aggregation for these communities. So that's also a new type of forecasting products, etc., etc. One last important point is this new paradigm in power system operation. I'll have a last slide on that. There are new ways we want to operate the system. It's driven by renewables, but it's also maybe progress more generally in the system operation business. And you will see that it calls for new forecasting products. I have this pillar here, which is about end users. And that's clear. I told you it's a problem-driven approach that we have. So the end user expressed needs is a big driver for the development of this new forecasting product. Finally, I think we have to realize also that a big push has come from the R&D side. R&D, George mentioned that forecasting was quite mature, but still R&D has been extremely active over the last 20 years. George was showing the increase in papers, but it's not only that. I mean, we can see it in many different contexts, in different companies, in different bodies, professional bodies. Forecasting of renewable has increased in terms of presence in all the industry and the R&D. So the R&D there has been very active and has been pushing always a new concept. Some have been adopted very easily by practitioners and the industry, and some of them maybe have not been accepted yet, you could say. So if we were to focus, for instance, on the case of high resolution, I'll show you some high resolution forecast afterwards and we'll discuss that. But just to put it into perspective with these pillars, when we talk about high resolution forecast, there is definitely a contribution from the regulatory and market framework. I was telling you there's going to be higher temporal resolution in electricity markets, and maybe renewables should contribute to ancillary service provision in the future, especially offshore wind farms. So then we need a higher resolution forecast. All these prosumer markets also will call for higher resolution forecast. Then when we talk about technology, again, if we zoom on the offshore wind farm control and maybe combine with storage, it is clear that we need much higher resolution forecast for this kind of task. Classically, the forecast would have an hourly resolution, maybe in some cases 15 minutes resolution, but ideally, if you wanted to operate offshore, large offshore wind farms, possibly coupled with storage, the kind of time resolution we're going to talk about is more 1 to 5 minutes resolution. Same goes with the end user needs. Personally, in my research and work on consultancy, I've heard a lot of expression of interest for higher resolution forecast, but I'm not the only one. I had an example here that I put. It's Copenhagen Airport. Copenhagen Airport wants to be one of the first airports in the world to be carbon neutral in terms of ground operation. They will invest in solar, in storage, in new ways to operate their system as a nice and clever prosumer. But then for them, it was clear that if they do that, they need high resolution forecast. They are talking of 1 to 5 minutes forecast for PV to operate their system locally at the airport. And then the push from the R&D side, actually, I can tell you that this idea of high resolution forecasting, it's been the dream for most of the people on the R&D side for 25 years. There's been a lot of models. For those who were there at the time, we're talking about MM5. There's been other type of models. It was maybe not as good as we wanted, and it was extremely computationally expensive. So there's been a bit of a down period, but now it's coming back very strong with a push from the R&D side. And this is what I will focus on in the next slides. So when we think of high resolution, it is an extraordinary case to discuss what's the difference between what we produce as forecasters and what become a forecast product that the forecast users may be able to use. So look at an offshore wind farm here. It's a visualization of Horns Reef. It's the first large offshore wind farm we had in Denmark, 160 megawatts. It's getting quite old now, and there's much bigger wind farms, but still at the time, it was amazing. And a company like WIFL, which is part of the project, but there are others, they can provide very high resolution weather forecast for a place like Horns Reef. So I'm talking about spatial resolution in tens of meters, 50 to 100 meters maybe in a more operational setup, and temporal resolution of approximately 30 seconds. So that's extremely high resolution in space and in time. So you're producing a lot of data out of these models, but does that mean we can really directly use this data and this information in a good way? Maybe not. It's actually a lot of work after that. And this work, to get to a forecast product, it's most often done through post-processing. And I think kind of post-processing has been something that people have heard a lot over the last few decades if they worked with forecasting and renewable energy forecasting. But normally post-processing is seen as something for improving forecast quality. We've all been obsessed, you know, there are biases in the forecast. I want to use machine learning to improve my forecast, etc. But actually, if we think of this product-driven approach, post-processing is the way to grab all the information out of these models, these physical models, or any kind of data source, and transform it into a forecasting product that is tailored to the need of the forecast user. So I have an example, again, for some offshore wind farm like Horns Reef. You see on the left this plot, that would be some raw output from the models. So this model here is called GRASP, it's in red. That's high resolution forecast. In blue, you would have the lower resolution forecast from ECMWF, and in black, you have the observation, right? But most of the forecast users, they wouldn't want to get this red curve as a forecast. They would either want that this forecast come into the single value traditional forecast, maybe at higher resolution. So you would have to post-process that and remove biases at this time resolution. But some others have also expressed the need for viability forecast. They would like to know within a certain time period how viable the wind power production is going to be. Also in the past, there's been a lot of discussion about REMs, and that's the same. Then you need to post-process this information to predict REMs. And finally, something that we've seen that seemed to be quite interesting and important for offshore wind farm is to predict what could be potential minimum and maximum production within certain periods based on this super high resolution information. There's also the probabilistic side. George has insisted on the fact that probabilistic was there to stay in renewable energy forecasting. quite a number of us, our colleagues and I, have made a contribution towards probabilistic forecasting. And this is, for instance, a classical visualization. I mentioned visualization before. So this would be predictive marginal densities here, instead of having the classical forecast that are single valued for each and every hour in the future, and just giving a single value as what is we expect to happen. So that's in red in this figure. Then you have these prediction intervals that give you a range of potential power production with a certain probability that we call nominal coverage rate, right? So this concept has been pushed forward maybe 20 years ago in energy forecasting, and now it's everywhere. We really see this kind of visualization. It's a standard. It's available to industry if they want to use it. Maybe some forecast users are very sensitive. They love this information. Some others are not so keen. But we see here a new forecast product that has become something that is there in the industry. But even there, actually, the probabilistic forecasting doesn't stop at this simple, let's call it simple, it's not that simple, but still, these marginal predictive densities. For some forecast users, they say, yeah, but for me, it's not enough, or it doesn't fit the way I'm making decisions. I would prefer to have scenarios. And the scenarios are here on the right. That's one representation. Instead of giving a range of potential outcome for each and every hour in the future, we give trajectories. So we give equally likely trajectories in the future for the power production. And that's very nice because this can be plugged into decision-making tools like a Monte Carlo simulation tool. And then you can actually look at the type of decision you would make based on different potential realization for the future power production. But there also, we've seen that many more methods for decision-making under uncertainty are being pushed forward. Some talk about robust optimization, some talk about change constraint optimization. Some people focus a lot on the spatial dependencies in the uncertainty. And then they have been asking for new types of forecasting products that would look a bit more complex and maybe a bit more funny. They can take the form of polyhedra that you see here on the left, or of ellipsoid that I didn't represent here. But these kind of objects would be classical objects that mathematicians would use if they consider multivariate uncertainty, so uncertainty with dependencies between location or time instant, that you can actually use as input directly into some stochastic optimization methods. Finally, George mentioned something. Oh no, not finally, I have another slide afterwards. But here I want to insist on the fact that we can also in the future consider data and the forecast themselves as products. We really see an interest in more data sharing or collaboration, as George was insisting on. And also now there's so much data that is being collected and that could be used as input to forecasting. We need to find ways for people to share information or at least collaborate in the forecasting exercise. So one of the key focus area that we have in the SMART4RES project, and I think it's in the air in different type of project, is to define some collaborative analytics framework so that different actors are willing to share data or work together to improve forecast. And eventually, if we do that, it should improve social welfare for everybody. You have an example here. You may consider this wind farm 1 in the middle in blue. And this wind farm 1 believes that it could improve forecast substantially by using power data from wind farm 2, maybe weather forecast from wind farm 3, and then radar images from a met station. And what is going to be organized is to have some kind of market for information. And in this market, the wind farm 2 will share power data, the wind farm 3 will share weather forecast, the met station will share radar images, but then we need to find optimal payment for that. And that's actually a quite difficult question. Similarly, it's not been represented here, but wind farm 2, wind farm 3 may not want to directly share the data because there's privacy concerns, there's a competitive business interest. And so then we have to find ways to actually incentivize this collaboration without affecting the integrity, you may say, of the information of these people. And there's different type of methods today that can be used by adding noise, by distributing the computation, so that we have the full benefits from collaboration without revealing the information of all the agents in this game. So finally, there's also one aspect that is very interesting, is that as we go towards more active distribution grid management, we can have very localized forecasts at the distribution grid level, but then we also need to have aggregated forecasts for RES and load, for instance, at the distribution grid level, and they will have to be coherent. So there are new type of forecasting methods that ensure that you can have coherent forecast at different level of granularity. And eventually, based on that, and by integrating the grid within the forecast methodology, you can, for instance, issue forecasts for flexibility of an active distribution grid. And you have a representation here on the top right in terms of active and reactive power. So there's really a lot of room for new forecasting products. And I can tell you, while we believe renewable energy forecasting is mature, there's so much more work that can be done. I give the word back to George, who wanted to give you takeaway messages.
So thank you, Pierre. Oops. Yep, the previous slides. Okay, thank you. So what can we conclude today, actually? Smart4RES is a collaborative project where we try to improve the forecasting technology, not so much through incremental approaches, but with some new ideas. So the first takeaway message is that there is a big focus on improving weather forecasting, but the work we want to do and we focus the research priorities is oriented to improving the variables which are sensible for the weather-dependent renewables. Then we want to develop an approach which permits a kind of convergence of the technology, a kind of seamless approach, because this enables, on the one hand, to simplify the model chain while considering the big quantities of data from different sources that we can have today. Finally, we want to exploit the possibilities from data science techniques and artificial intelligence to develop alternative forecasting and decision-making paradigms where the tuning and the calibration of the forecasting models is considering also not only the accuracy, but also the value that the forecasts bring to the end user. And why not simplify even more the whole process, the whole model chain using these data science approaches. Finally, as Pierre mentioned, it is important to rethink the whole value chain and think where are the areas where we can improve predictability, and one of them is definitely data sharing. And for that, one takeaway message is that there is a different way, an alternative way that we can consider data through for example, concepts like data markets, which permit to extract the full value that we can have from the available information. So maybe next slide. So the consortium of Smart4RES is quite limited. We have 12 partners, but we are quite open. And if you want to be in contact with us, we have developed a reference group of industrial partners, and you are invited to contact us if you want to make part of that, or if you want to share data that can be used for evaluation of new models, etc. We are inviting you also, if you want to complete a questionnaire, which is given at this link, on the way you are using forecasts and the way you use forecasting decision making for different inside different tools for power system management, renewable power plants management, trading, etc. Then next slide. So if you want to have more information about the project, we organize a series of webinars. There will be a second episode in October on RES forecasting and data marketplace, a collaborative framework where we will develop more in detail what Pierre presented here and myself about the data sharing. and also a third episode by the end of the year, where the objective will be to show methods that permit optimization of participation of renewables, generation in electricity markets, new opportunities, and the role of forecasting. You can subscribe at the newsletters of the project and follow us at Twitter or LinkedIn, or contact us through this email address. So I would like to thank you for participating, and we are open to questions.